You clicked on this video because you saw a headline claiming 500,000 token context windows on a single 48 GB graphics card. That sounds like a miracle, but the real problem is that your hardware cannot actually do that without breaking. If you try to run that workload today, you will hit a wall that no amount of money can fix with just more memory. I am going to explain why the true limit is not your VRAM capacity, but your memory bandwidth and compute density, and reveal the specific architectural tricks that make this speed possible without destroying your model's intelligence. Let us start with the most common misconception in the industry. When we talk about context windows, we instinctively think about storage space. We imagine a giant hard drive where every token takes up a slot. If you have 48 gigabytes of video memory, you assume you can fit a model with a massive context window as long as the total number of tokens stays below that limit. This is a dangerous assumption because it ignores how the underlying mathematics of attention mechanisms actually work. The memory required to process a sequence of text does not grow in a straight line. It grows quadratically. This means that if you double the length of your text, you do not just need twice the memory. You need 4 times the memory to store the key value cache, which is the data structure that allows the model to remember everything it has read so far. Here is the thing that changes everything. When you push a 48 gigabyte card to handle a 500,000 token window using standard architecture, you are not filling up your memory. You are choking your memory bus. The system becomes bandwidth bound. This means the GPU cores are sitting idle, waiting for data to be fetched from the memory chips. The speed of your generation, that 21 tokens per second benchmark, is dictated entirely by how fast data can travel across the memory bus, not by how much data you can store. Adding more video memory does nothing to solve this because the bottleneck is the speed of the highway, not the size of the parking lot. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This reality explains why so many reports from the community show failures. You will see developers trying to run long context models on 48 gigabyte cards and hitting out-of-memory errors or crashing their systems. This is not because they exceeded the total capacity of the card. It is because the fragmentation of memory bandwidth required to process the full context window simultaneously creates a traffic jam that the hardware cannot clear. When the attention mechanism tries to calculate relationships between every single token in a 500,000 token sequence, the data movement required saturates the connection between the processor and the memory. The system grinds to a halt. So how do we get around this? The answer lies in a framework called InfiniteHiP, which demonstrates that achieving massive context windows is less about hardware capacity and more about algorithmic efficiency. This system achieves 3 million token contexts on a single 48 gigabyte card, not by expanding memory, but by dynamically pruning tokens and offloading the key value caches to the host random access memory. This is a fundamental shift in how we think about inference. Instead of trying to keep every single piece of information in the fast video memory, the system intelligently discards tokens that are no longer relevant and moves the heavy data structures to the slower but larger system memory. Now consider the implications of this approach for your own work. If you are a junior engineer or an early career developer building production-grade applications, you need to understand that the default settings on popular tools are often set to fail at scale. You might see a tool like Olema or Unsloth report that it can handle a certain context length, but that is often based on a fixed size that ignores the quadratic scaling of attention. When you try to push beyond that limit, the system does not gracefully degrade. It triggers CPU spillover or crashes entirely. This proves that fixed context sizes are a trap. They ignore the physical limits of the hardware and the mathematical reality of the attention mechanism. The most valuable insight you need to take away is that sliding window and retrieval augmentation are not just optimization tricks you can add to a project for fun. They are mandatory architectural constraints for any system running on consumer or prosumer hardware with limited video memory. Without these interventions, the quadratic growth of the key value cache physically exceeds the memory bandwidth required to sustain inference on long sequences. You cannot simply load a larger model or context window into the same video memory pool and expect it to work. The performance will degrade non-linearly, and you will lose the ability to generate text in real time. This leads to a critical career-relevant engineering trade-off. For local coding workflows or any production environment where you need high token throughput, the optimal strategy is to shift from context window maximization to retrieval, augmented generation. This approach avoids the memory bandwidth bottleneck inherent in full context attention mechanisms. Instead of feeding the entire history of a conversation to the model, you retrieve only the most relevant snippets based on the current query. This keeps the active context window small, allowing the GPU to operate at peak compute density rather than getting stuck in a bandwidth-bound regime. However, we must also be honest about the costs of this efficiency. The InfiniteHiP framework reports an 18.95 times speedup, but this performance relies on aggressive token elimination. This means the system is actively deciding which information to throw away. For complex coding tasks where every single token carries semantic weight, this risk of context loss is significant. You might lose the ability to reference a function definition from 3,000 tokens ago if the pruning algorithm decides it is no longer relevant. The 21 tokens per second benchmark is likely achievable only under specific pruning conditions rather than full context inference. Consequently, the narrative that raw VRAM is the only limit is false. Achieving massive context windows is a battle of algorithmic efficiency. Current systems still struggle to balance full context fidelity with the memory bandwidth required for real-time generation without sacrificing accuracy. If you are building a system that requires perfect recall of a massive codebase, you may need to accept slower speeds or invest in hardware with significantly higher memory bandwidth. But if you can tolerate a degree of approximation, then architectural changes like sliding windows and retrieval augmentation offer a path forward that raw hardware upgrades simply cannot match. The lesson here is that when you design for scale, you must design for the physics of the machine, not just the capacity of the memory. You must respect the bandwidth limits and the quadratic scaling of attention. By understanding these constraints, you can build systems that are not just theoretically possible, but practically viable in the real world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.